weather. There are four seasons that we all know and love, which is, of course, spring, summer, fall, and winter. So, we all know these four seasons exist, but if I tell you there's another season, or so you call another weather, which is, of course, space weather. Have you guys ever heard of space weather? Well, it is really an interesting topic to talk about, and in today's video, I'm going to be covering about it. So, let's get into it. So, guys, welcome back to a new video, and in this video, yes, of course, we're going to discuss about space weather. So, without further ado, wasting any of your precious time, let's get into it. So, from start, minor storms are, of course, relatively common, and a major storm may occur once or twice per decade, of course. So, of course, this is space weather, of course. So, like solar superstorms occur once every 100 to 200 years. So, what they're trying to say here is really about solar storms, which means it's about the sun. Okay, solar means sun energy, of course. So, the Earth's magnetic field protects us from them. Okay, yeah, that's a fact. So yeah, these particles could have impact or create havoc, produce a variety of physical effects and technological impacts. So as we know, our technological items are made out of many things. So if it really affect us today, it would be really costly, and I will explain about that at the end. Okay. So the solar emissions, of course, interact with the Earth's geomagnetic field and upper atmosphere, which is of course called the exosphere and the thermosphere, and also known as the ionosphere. So, okay, the exosphere means is the outermost layer of the Earth's atmosphere. So it's like the top, like the highest layer. Okay. So yeah, the X layer is very thin, and the density is so low that molecules are collisionless, so they can't collide with each other. And the exosphere also contains many satellites orbiting the Earth, like many satellites. And then the thermosphere is the layer in the Earth's atmosphere directly above the mesosphere and below the exosphere, so it's in between both. So within the layer of the atmosphere, ultraviolet radiation causes photonization, which is of course a very hard word to say, but yeah, of molecules creating ions. The thermosphere thus constitutes the larger part of the ion. So really, the thermosphere is really stopping the ultraviolet radiation from entering on Earth, because creating ions, and the thermosphere constitutes the larger part of the ion, of course. So it's called photonization. So, um, phenomena such as aurora are occasionally seen in the thermosphere. The International Space Station orbits in this layer of atmosphere, so it's in the thermosphere. Okay, guys, if anybody asks you in school, where can you find the International Space Station, in which layer of the atmosphere? Yeah, you already know because you watched this video. And of course, it's located in the thermosphere, which is in between the exosphere and the mesosphere. So, guys, after this very short break or intermission, we shall continue on what is space weather. I mean, not what is space weather, how it really happens, and the solar cycle progressions, and then the satellites, and then um, the radio blackouts, and then the GPS, the global positioning system, and then the power grids, which is of course what I'm going to tell you how it really will affect us, as you may not know the Carrington event, but yeah, I will explain about that at near the ending, which is of course the power grid operation. And then finally, we'll go to the impacts on humans. Uh, so yeah, after a short intermission, we shall continue these things. So guys, that was my short intermission, and now I will be explaining about space weather, how literal space weather happens. Okay, so literally, space weather happens every 11 years by the sun's magnetic field flips, of course. So the north and the south pole of the sun trade places, so the solar activity rises and falls. And so the level of radiation from the sun, solar radiation, and ejection of solar material, number and size of sunspots, solar flare, and coronal loops all exhibit a synchronized fluctuation. So synchronized fluctuation means like synchronized means same, and fluctuation means increase, of course, from active to quiet to active again within a period of 11 years, of course. So right now, I'm projecting to you a chart of a solar cycle progression and how it really will affect us. So man must send people to any other planet or moon or Mars by before like 2024, because after that it's a peak of solar levels and it will really be dangerous. So as you can see, I've circled the part where man is very dangerous to travel to space. So yeah. And so for many centuries the effects of space weather were noticed but not understood. Displays of auroral light have been observed at high latitudes, and in the 1950s, the term space weather was first used, which is about 71 years ago. And as modern civilization are more integrated and connected, we become more dependent on continent-sized electric power distribution grids, global satellite communication and navigation systems, and more on the military side, and imagining the how really space weather affects us. So a really powerful solar storm could really wipe out millions or even billions of people off the surface. But up in the orbit, things are even more dangerous. Powerful solar winds caused by high-tended solar activity could easily knock out GPS and telecommunication satellites. So GPS could easily be knocked out 50 meters on your actual direction, destination. So we're going to touch about the space weather impact on technological infrastructures and mainly satellite communications like radio blackouts, GPS, power grid operation, and high frequency radio communication. So there are different types of solar activity that are common concern for critical infrastructure operations, which are solar flare, solar radiation storms, and geomagnetic storms. And so, how are satellites really affected by this? So let me just give you a summarized version of how satellites are really impacted. So satellites during a solar radiation storm are more likely sensitive, and electronic parts will be hit by charged particles, and it will continuously striking of ions can damage solar cells and degrade wiring and other equipments. And so these impacts to satellite-based navigation systems, which we all use in our everyday mobile phones, will become less accurate. So guys, other impacts are also experienced on the electricity grid, like satellite and cellular communication systems. And the solar radiation also could threaten to even, stop us from robotic or manned spaceflight, like to Mars. So guys, really the whole asset of a civilization spacecraft at geostationary orbit is around estimated to be greater than $200 billion, which is huge, of course, in space assets. So, guys, after this very short intermission, we shall go to radio blackout and then power grids, and then we shall go to GPS, and then impacts on humans. So I hope you guys can understand what I'm saying and catch it. So I'll see you guys after this short intermission. So guys, and now we're going to continue with radio blackouts and power grid operations if, of course, solar flare occurs. So, for radio blackouts, when a solar flare occurs, ionization is produced in the lower, more dense layers of the ionosphere, which is, of course, called the thermosphere, and radio waves that interact with electrons in layers lose energy due to the more frequent collisions that occur in the higher density environment of the D layer, and this can cause high frequency radio signals to become degraded or completely absorbed. Okay, so this results in a radio blackout, which is of course the absence of high frequency communication. So solar flares which trigger radio blackouts very quickly and affect radar, ground and space-based communications including high frequency HF communication and the GPS network causing loss of lock. So, moving on, we have power grid operations, but before that, we're going to show you, as you can see, I'm projecting a graph here, not a graph, the image here, about the GPS growth. Also from LASP Media Workshop / Boulder. So this is a research on Industrial Technology Research Institute by ITRI from March 2005, and yeah, it is from March 2005. So 2003 was what, 13 billion. I mean, the expected growth. 2008 expected was 21 billion. Then 2017 should be around almost 1 trillion, but around 750 billion dollars. So of course, now moving on to power grid operations. A geomagnetic storm is a temporary disturbance of the Earth's magnetosphere caused by solar wind, shockwave, and/or cloud that magnetic field that interacts with the Earth's magnetic field. So during this time, guys, electric currents in the magnetosphere and the ionosphere experience large variations. So these variations in this currents and geomagnetically induced currents, or GIC, which is called geomagnetically induced currents. So in conductors operated on the surface of Earth like electric transmission grids and buried pipeline. CIG, which is of course, I already told you that earlier, can cause problems such as increased corrosion of pipeline steel and damaged high voltage power transformers. So GIC are also one possible consequence of geomagnetic storm, which may also affect geophysical exploration, surveys, and oil and gas drilling operations. So it was suggested in 1859, as I said, the Carrington event. It has been suggested that a geomagnetic storm on the scale of solar storm of 1859 today would cause billions or even trillions of dollars of damage to satellites, power grids, and radio communications, and could cause electrical blackouts on a massive scale that might be repaired for weeks, months, or even years. Imagine, guys, years without electricity. Man, that would be so hard. We would be living the Stone Age if that Carrington event happened today. Of course, Carrington event was named by a person called Robert Carrington, and he's the guy who suggested this. I mean, not suggested it, he was talking about this, okay? So that's about it, okay? So after this, we're going to cover GPS communication and then impacts on human. And then right after that, it's the ending of the video. So I shall see you after this final intermission. So let's get into it. So guys, finally we will be ending everything on these two subtopics, which is of course global positioning system, which is of course GPS. So GPS is really the use of signal and dual frequency satellites like radio navigation systems, which of course receivers are now in nearly every cell phone. I mean, in fact, GPS in like nearly every cell phone and cars. Even cars have built-in GPS. Can you even imagine that? I mean, in our calm conditions, single frequency GPS systems can provide our information with an accuracy of a meter or less. GPS radio signals travel from the satellite and the receiver on the ground and passing through the Earth's ionosphere. And the dual frequency GPS systems can provide position and information accurate to a few centimeters, and charged plasma of the ionosphere bends the path of the GPS radio. Well, that was the GPS, of course. How it really makes it less accurate. The space weather from the solar flare from the sun really makes it really inaccurate. Finally, we have how it affects humans. Well, effect on radiation, of course. Like space weather was certainly overlooked at the start of the space age, of course, but it is being taken increasingly seriously, of course, and both in terms of terrestrial impacts and for space exploration, yeah. And radiation from space weather can be very harmful to our human bodies, like ultraviolet radiation, of course, and which is why astronauts need to be really careful because it can damage their cells, which can lead to range of problems, including weakening muscles or causing memory loss. The longer they're exposed, the more harm is done. Like, let's say what happened in Ukraine, like Chernobyl, cost literally a lot of lives, like that, but it's in space. So solar proton events can also produce elevated radiation aboard aircraft flying in high altitudes. Although these risks are small, flight crews may be exposed repeatedly, and monitoring of solar proton events by satellite instrumentation allow exploitation to be monitored and evaluated. So eventually flight paths and altitudes to be adjusted to lower the absorbed dose. So it really can cause a lot of damage in human, but mostly in space because really doesn't affect people on Earth because our ozone layer is protecting us. So anyways guys, I'll see you guys in that video. Peace out and bye bye.